Hello, prelim chemistry students. Today we're here to talk about the mole, one of the most important concepts in chemistry. This is one you're going to want to make sure you know this concept. As you can see just here in our Module 2, Introduction to Quantitative Chemistry, we are looking currently at chemical reaction stoichiometry and the mole concept. Those first two inquiry questions are going to be combined in our working through this module. All right, so what do we mean when we're talking about the mole? Okay, we don't mean one of these cute little fellas just here. All right, so let's start with a little bit of history, people. A French chemist by the name of Gaudreau, he actually established the law of combining volumes of gases. It's a little bit of a party trick, but what we found is that when we combine gases together and we have a reaction occur between those gases, those reactions always occur in such a way that the volumes of those gases are simple whole number ratios. Now, that wasn't something at the time they were able to establish as being true with non-gas-based reactions. But it was a hint for chemists at the time that there is something going on. All right, a little bit later on, we have another physicist by the name of Amedeo Avogadro, commonly called avocado by chemistry students when they're first introduced to him. He actually refined Gay-Lussac's law, and the reason why that was a problem is that at the time, all gases were assumed to be one atom. And so what was happening by combining one volume of hydrogen with one volume of chlorine, we were producing 2 volumes of HCl in the above example, shown just here. And each volume of HCl had 1 atom of hydrogen, 1 atom of chlorine. So the understanding of what was going on seemed flawed. What Avogadro did is he actually linked that to the number of particles. Hydrogen and chlorine have to actually have 2 particles. And he was able to establish that the reaction occurred because the number of atoms were conserved across the reaction. And this, started to really let us establish the idea that chemical reactions are happening in a quantitative fashion. Combining this, at the time, we also had the idea of relative atomic mass. We have John Dalton, of the billiard ball model of the atom. In his studies of the elements across the periodic table, and bear in mind the periodic table was being established at the time, he tried to base a scale off the mass of atoms, with hydrogen being 1. Had a lot of trouble establishing and measuring that scale, to be honest with you, because it's hard to work with gases like hydrogen. Another chemist by the name of Berzelius based his own scale off of oxygen, which is a lot easier to work with, and it's quite handy because it reacts with most metals on the periodic table, and as you know, most of the periodic table is metals, and oxygen still reacts with many of the non-metals as well. And on his scale, he assigned oxygen a mass of 100 just to make the math easy, but his mass of 100 didn't actually stick. But others later on expanded on this, and they kind of wanted to keep the idea of hydrogen having a mass of 1. And so what they did is they assigned oxygen a mass of 16, which is why it has the exact mass of 16.00, and scaled the masses of all other elements off of oxygen. This gives hydrogen a mass of 1. It's one of those things to take note. Have a look at the relative atomic masses on your periodic table when you're next looking at it. And then, of course, another idea was percolating around. This is the idea of equivalent mass, the idea that chemical reactions are happening because of equivalent masses of substances are actually reacting together. And this is kind of where the mole got its name. It actually got its name out of a translation of a German unit for equivalent mass, first coined in 1897 by the chemist Wilhelm Ostwald, pictured on the right with his awesome beard. However, I will point out that the idea of equivalent mass has been cited at least 100 years earlier to the work of Ostwald. With all those ideas coming together, what the mole is a measure of a number of particles. And our gold standard for that is that when we have exactly 12 grams of carbon, we have 6.022 times 10 to the 23 atoms of carbon. And you can understand how it took a little while to establish this, because we were first trying to work it out with gases. And hydrogen is an absolute pain to work with as a gas, because it will actually go through many containers. Like, you can't hold it in balloons, for example. You fill up a balloon of hydrogen, yes, it'll float away just like a helium balloon, But the atoms are so small, they'll actually go out through little microscopic pores in the surface of the balloon and it'll deflate overnight. Alrighty, so what exactly is the mole? Well, the mole is, in chemistry, it's an amount, just like a baker's dozen, where a baker's dozen is 13. When chemists talk about a mole, they're talking about a specific number of atoms in a reaction. In this case, 6.022 times 10 to the 23 particles. All right, and I say the word particles because particles is really just a way of saying things, because we can talk about matter in terms of moles of atoms or moles of molecules. And sometimes even electrical engineers will talk about electricity in terms of moles of electrons. So it's one of those sort of things we can actually establish that when we're talking about really large numbers of particles, like we often are in chemistry, all right, we need a way to talk about that. So we can talk about that using simple whole numbers like 1 or 2. And so in that case, the mole is just like a baker's dozen or a pair or a ream. That's 500, by the way, for those of you in the know. That's why when we talk about paper, reams of paper, they come in sets of 500. Okay, and why do we use the number 6.022 times 10 to the 23? Well, that is the number of particles that is found in 1 gram of hydrogen. All of those relative atomic masses, not only are they scaled to actually be the relative mass of the atom, they're also scaled to be the relative mass of 6.022 times 10 to the 23 atoms in grams of a particular element. Now, I will also just finish up. Sometimes when chemists are talking about the mole, and we're talking about the idea of 1 mole being 6.022 times 10 to the 23 particles, we call it Avogadro's number in honor of the chap shown on the right just here. So that brings us to a close for our video just here. I do hope you have a better understanding of what the mole is right now. Thank you for watching this video. Feel free to comment on our Google Classroom if you have any questions. Let's get on with the lesson. Bye.